Anyone of you tell what is conduction, what is convection, what is radiation? Yes, ma. Anyone? No one knows what is conduction, what is convection, what is radiation. Am I audible?
So conduction was transfer of heat from within the body, like within the boundary from one molecule to
Okay,
another.
very good, very good.
Convection was like heat transfer of one body to another body from like liquid or air, something like that.
Sir,
One
there's a
body to another
medium for
fluid.
certain
Uh,
convention.
yes.
Sir, there's a medium for convention, sir.
Yeah,
Medium.
yeah. Okay, okay. Actually, convection is a combination of conduction and advection. Okay, so the two words combined together, convection has come, right? It is a combo of conduction and advection. Okay, so what happens is the heat is transferred from the top surface to the liquid, and you will be having a fluid motion of the liquid. Fluid motion. It involves fluid motion. uh, that is bulk fluid motion of it involves, so that what happens is heat is carried away by the fluid which flows at a certain velocity. Okay, that is convection. And in case of radiation, heat transfer by means of electromagnetic waves, mainly due to the temperature difference. Okay, and a very practical example for radiation is getting that is earth get the heat from the sun. Okay, so sun is very hot, and usually we will be getting the sun's radiation to the earth's surface. Okay, without any medium. Okay, so whereas in case of solids, in case of conduction, what we have is the heat is transferred from one molecule to another molecule. Okay, so the heat transfer from one molecule to another molecule, and it also depends upon the thermal conductivity of the particular material. It is a property of the material, thermophysical property, okay, of the material, which gives us an idea about the conductive nature of the particular substance. Okay, and in case of convection, as I mentioned earlier, right, either the you will be having a hot surface and a cold fluid, or you will be having a uh, cold surface and a hot fluid. Okay, so the hot surface and cold fluid is the practical example. What is a practical example? I told you. What is a practical example? Internal combustion engine fins, two-wheeler fins, right? Two-wheeler engine fins. All of you are listening.
Yes, sir.
Am I
Yes,
am I
sir.
audible? Only two or three are answering. There are a group of 70 students.
Yes, sir.
Okay. See, what is the example of a hot fluid and a cold body, ma? Anyone? Can you tell me one example? Hot fluid and cold body. Shreya, who is that Shreya? Anirudh, Aditya, Mohilan. Anyone of you can answer? Are you there?
Yes, sir.
Yeah. What is the example for hot fluid and cold body? The fluid or the steam which passes through the steam pipe, okay, to the turbine. So the steam will be at a very high temperature of around 400 degrees, okay, whereas the pipe material will be at a lesser temperature. Okay, so usually the pipe is insulated, so that what happens is the pipe should not give away or dissipate the heat to the surrounding atmosphere. Okay, so flow of steam through a pipe is an example for the flow of a fluid or a hot fluid and a cold body. Is it okay?
Yes, sir.
Am I correct?
Okay,
Am I
sir.
correct or not? See, please correct
Sir.
me if if I say some wrong examples, because you people, you have to know the concept. Basic concept is very important. And similarly, yeah, that's what it was mentioned here. Heat transfer is here is due to a temperature gradient in a stationary medium or media is conduction. Heat transfer occurs between a surface and a moving fluid when they are at different temperatures. That is convection. And in case of radiation, occurs due to emission of energy in the form of electromagnetic waves by all bodies above absolute zero temperature. Net radiation heat transfer occurs when there exists a temperature difference between two or more surfaces emitting radiation energy. Okay, so in thermodynamics, you might have studied about that is the zeroth law, first law, second law, etc. Right? Which gives us an idea about thermal equilibrium between bodies, and which gives us an idea about that is change in internal energy. Okay, or we know that Q minus W, which is equal to del U, and second law of thermodynamics gives us a direction of heat transfer, right? And the second law of thermodynamics also tells us that there should be heat addition and heat rejection. All the heat energy is not converted into useful work. Okay, so you discuss so many things in thermodynamics. The basics of thermodynamics, again, it's very important. Okay, especially when it comes to heat transfer applications. Can anyone say the first law of thermodynamics? Zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics. Anyone? Charles is there. Charles,
Yes.
are you there? Yeah. Can you tell me what is zeroth law of thermodynamics, first law of thermodynamics, and second law of thermodynamics? Actually, there are two statements: Kelvin Planck statement and Clausius statement. Generalized statement also you can say in case of second law of
First
thermodynamics.
class energy conservation, but I
Yeah.
don't remember the statements exactly.
Okay. In a cycle, the net heat transferred is equal to the net work done, or work done is equal to Q minus W, which is equal to del U, or Q equal to W plus del U. Or in other words, the heat transferred, which is equal to work done plus change in internal energy. Okay, so that's what usually the first law of thermodynamics states. And in case of second law, it gives the direction. Okay, what is a refrigerator? What is a heat pump? What is COP and all? It is defined by the second law of thermodynamics. It states that all the heat energy cannot be converted into useful work. Okay, some portion of heat energy is rejected to the surroundings. Especially Kelvin Planck's statement and Clausius statement, when you put together in a combined manner, it is impossible for a device to convert all the heat energy supplied into it into useful work. Okay, and there will be some heat rejection. And similarly, it is impossible to maintain a body at a lesser than that, at a lesser temperature than that of the surroundings. Okay, unless otherwise you have a device to do it. That is the thing which is usually the refrigerator and air conditioners does. Okay, so the refrigerator maintains the body at a lesser temperature, but you need the work input which is given in the form of running the electric energy is needed to run the compressor. In all our houses, we have the refrigerators. So what happens is the refrigerator needs electrical energy to run the compressor. The compressor in turn passes the refrigerant or pushes the refrigerant into the evaporator coils, and it takes the heat energy. Okay, so if you want to maintain a body at a lesser temperature, then you have to need the external work aid. Okay, so these are all some of the things. Okay, so the first law of thermodynamics, as Charles pointed out, first law of thermodynamics deals mainly with the conservation of energy, whereas the second law gives us an idea about the direction of heat transfer, right? The direction of heat transfer, that's also very important. Okay, so heat transfer is important to industrial and environment problems and processes. All energy production and conversion processes involve heat transfer, even in electric power generation. That's what I told you in the very first class, bursting of tubes. It's also yeah, there also you will be having this that is the idea of heat transfer. Unless otherwise you have the idea of critical radius of insulation, you will not be able to manufacture the cables. Okay, electrical cables. So, and similarly in some applications heat transfer rate is maximized, while in other cases it is minimized. Okay, so where we have to maximize the heat transfer and where we have to minimize the heat transfer, it's also important. I have told you two examples. One is the practical cable, the other one is uh, the insulation which is given to the steam pipe. So in case of steam pipes, why insulation is provided, ma? In case of steam pipe, why insulation is provided? Anyone?
So no steam should leak.
Sir,
Yeah.
loss of heat, sir. To
Yeah,
avoid loss of heat.
to avoid loss of heat. See, what happens is usually the steam pipes will be exposed to surrounding atmosphere. Okay, if it is exposed to surrounding atmosphere when there is no insulation, what happens is the steam which flows inside 500 degrees C or 400 degrees C, it may be usually above the critical temperature. 374 degrees is the critical temperature, especially in case of steam turbines it will be flowing at around 400 to 450 degrees. So what happens is heat transfers easily from high temperature body to low temperature body. So heat transfer gets transferred to the steam pipe, and from the steam pipe, steam carrying pipe or steam pipe, and from the steam pipe when it is exposed to atmosphere which is at 30 degrees or even 40 degrees, look at the temperature difference, 400 degrees and 40 degrees. So naturally the heat gets transferred. So for that, the insulation has to be provided so that the heat is not dissipated to the surrounding outside. Whereas in case of electrical cables, what happens? It should be the other way around. The heat transfer rate should be maximum. See, two cases. One is the heat transfer rate should be minimum in case of steam pipe, whereas it has to be maximum in case of electric cables. In case of electric cables, why the heat has to be dissipated out? Why the heat has to be dissipated out, ma? I have told you about bursting of cables. See, practical applications are very, very important. See, due to the conduction of electricity by the wires, what happens is there will be internal heat generation. That internal heat generation has to be dissipated. Okay, if it is not dissipated well, then what happens is the wires will fuse, and or sometimes the burning of wires or arcing of wires or sparking will be taking place at the junction. So that what happens is you will be losing the electric connection, and you have to completely replace the cable. Am I correct or not? Even in iron boxes, often we change cables after 3 or 4 years. Am I correct or not? Am I correct?
Yes.
Yes, sir.
Yeah, personally, I experienced it. Okay, due to overheating, sometimes what happens is the cable catches fire. So these are all some of the things. So in that electrical cables, the heat transfer rate has to be maximum. So it has to be given to the surrounding atmosphere. So when you design some equipments, okay, whether the heat has to be retained, heat should be dissipated to the atmosphere or it should not be dissipated. Those things you have to consider. Then only you have to do, you have to go for design. And similarly yeah, these things I have already told you. Thermodynamics first law gives us some idea about energy conservation, and second law gives us about direction of energy transport, and fluid mechanics gives us an idea about rate of momentum transport, whereas heat transfer gives us an idea about rate of thermal energy transport. Okay, so this is very, very important. See, that's why thermodynamics and fluid mechanics, if you are so strong in those subjects, then it is very much easier for you to understand the heat transfer. Okay, and some of them, especially some of them in some of the universities, okay, they teach heat transfer like a mathematical subject. Actually, it's not a mathematical subject, please understand that. Okay, of course, numericals you have to solve more numericals here, but the concept is also very, very important. Especially in some cases, some mathematical professors also might join the heat transfer process to take classes. Okay, that's also there, but actually, it's not a mathematical subject, or it's numericals will be there, but don't think this as a mathematical subject, because it is concept is very, very important in a way when you study heat transfer subject. Okay, and similarly the heat transfer rate, um, it is given in joule per second, and heat flux usually it will be mentioned in watt per sorry, heat transfer rate is given in joule per second or watt. Heat transfer rate per unit length is given in watt per meters. Heat transfer rate per unit area is watt per meter squared, and temperature will be given in Kelvin only. Okay, and please understand that when degree C or Kelvin is there in the denominator, unit change does not affect the numerical value. This is very, very important. Okay, see, I used to say like this. Okay, when you substitute 100 degrees C minus 0 degrees C, the difference del T should be 100. When you substitute the same value in Kelvin, 373 Kelvin minus 273 Kelvin, it should be the same. Okay, so please understand that. See, some of them they think, sir, watt per meter degree C is given, I have converted into Kelvin, sir. Please don't do that. Watt per meter degree C is equal to watt per meter Kelvin. Please understand that. Okay, when it is in the denominator, this is very very important. Whenever I teach thermodynamics, okay, this is very very important because it gives us an idea about the temperature difference. Okay, it gives us an idea about the temperature difference. Okay, so don't put, sir, the temperature difference is 20 degrees, I have put 20 plus 273. Please don't do that. Okay, so 1 joule per kg degree C is equal to 1 joule per kg Kelvin. Similarly, thermal conductivity 1 watt per meter Kelvin is equal to 1 watt per meter degree C. This is very very important, and some of the students they used to do the mistake here. Okay, please don't do that. And these are all some of the relations. We know that Q minus W equal to del U. Okay, or first law of thermodynamics. From the first law of thermodynamics, we know that Q equal to W plus del U, or W plus du by dt, or in other words, heat transfer is equal to the work plus rate of change of internal energy. Okay, so in the basic heat transfer concept or the heat transfer equation, we are getting it only from first law of thermodynamics. Okay, see why I am taking this much time for the first 2 hours, because you have to know the basics. From the thermodynamics basics only you have to enter into the subject. Okay, and similarly thermodynamic reversible process, we know about TDS equation also. TDS, which is equal to PdV plus du by dt, and d by dt of TDS will be again, we know that d by dt of integral PdV. Integral PdV, we know that it is nothing but the work done. Okay, and then plus du by dt, where u is nothing but the internal energy, and T is time, P is pressure, V is volumes, S is entropy, and T is temperature. Okay, so there are three important laws which derives, or which defines, okay, conduction, convection, and radiation. That is Fourier law of conduction, Newton's law of cooling, and Stephen-Boltzmann law. Okay, so let us discuss. We know that we have discussed about conduction, convection, radiation. Now we know that in case of conduction, it is due to random molecular and atomic vibrational, rotational, and translation motion. Okay, conduction heat transfer is mainly due to this. High temperature and more energetic molecules vibrate more and transfer energy to less energy particles as a result of molecular collisions or interactions, so that the heat is transferred from one end to the other end. Okay, for example, if you have a sheet, if one end is exposed to high temperature, slowly the heat is conducted, or and that's what the heat is transferred from the high temperature molecule and more energy molecule to the less energy molecule. Okay, less energy particle. Okay, so this is the concept which is used in uh, iron boxes, especially the electrical iron boxes. They will be having a heating filament. Okay, so the heating filament is attached to the surface, and what happens is slowly the heat is transferred from the heating filament to the to the surface. Okay, so the iron box gets heated up. Okay, so when you switch it off again, slowly the heat that is the heating coil is switched off naturally. What happens is, depending upon the thermal conductivity of the material, the iron box cools down. Okay, so and the heat flux is usually mentioned in case of by watt per meter squared. Okay, and it is characterized by a transport property known as the thermal conductivity. Thermal conductivity is given in terms of watt per meter Kelvin, where or we know that, let us assume a small slab. Okay, let us assume a small slab of thickness L. All of you are able to see the small thing here, or shall I draw it?
It's clear,
All,
sir.
Yes, sir, we can see, sir.
yeah, now you can see here, at x equal to 0 the temperature is T1, and x equal to L the temperature is T2, and the thickness of the slab is say L. Okay, now what happens here is, at x equal to 0 T1, okay, the temperature is T1, and x equal to L the temperature is T2. Okay, so when the heat transferred, right, the heat transfer from x equal to 0 to x equal to L, usually it is defined by the Fourier law, where it gives us an idea. Qx is nothing but the heat flux, or Q by A. It will be in watt per meter squared, or per unit area, right? The area which is normal to the flow, okay, is assumed to be unit area, or the answer will be in watt per meter squared. So usually what happens is capital Q equal to minus Ka dt by dx, where K is nothing but the thermal conductivity, A is nothing but the area, and dt by dx is nothing but the temperature gradient, where dt gives the difference in temperature and dx gives the change in thickness, or the thickness of the slab, or thickness of the material which we take. Okay, so please wait, let me write it also, or other, yeah, here you can see here qx, which is equal to qx double dash into a, or which is equal to minus ka dt by dl, or why this minus becomes ka d and del t by l, because see what happens is we will be taking the upper limit, okay, at x equal to l and x equal to 0. So at x equal to l, temperature T is T2, and x equal to 0, the temperature is T1. Okay, so when you substitute it, we know that dt by dx equal to T2 minus T1, and dt is T2 minus T1, and dx is L. So when you substitute the dt by dx here, minus k into T2 minus T1 divided by L, which is equal to k into del T divided by L. And the total heat transfer area through a given cross sectional area A is given by Q. So this Qx is in some textbook they used to mention it as capital Q. Okay, Q conducted, which is equal to heat flux into the area. But in most of the cases, in most of the practical applications, we will be giving it in watt per meter squared. We used to assume this cross sectional area as 1 meter squared, and we used to calculate, or we used to give the Q conducted in watt per meter squared only. Okay, so the Fourier law, what it says is the heat transferred by conduction is directly proportional to the temperature gradient and the area which is normal to the flow. Okay, please wait. Let me write it. Yeah. All of you are able to see this? All of you are able to see this?
Yes, sir.
Okay, so what it says is, see, this is the Fourier law. The heat flux is directly proportional to the temperature gradient, or it is directly the heat transferred by means of conduction is directly proportional to the temperature gradient and the area which is normal to the flow. From that only we get the thermophysical property, which is nothing but the thermal conductivity. Okay, I have explained to you in the last class. Okay, I forget that. Okay, so from this we will be getting this. In the first module, we will be having small numericals also, because I don't do that numerical because it's very simple. If I will be giving you the thickness L, okay, and I will be giving you the temperature T1 and T2, and from that you can easily find out the heat transferred or heat flux. Okay, and now the second important property is the resistance. Okay, so now what happens here is usually what happens is we know that Q equal to Ka by L divided by Q equal to Ka by L into Th minus Tc, where Th is nothing but the higher temperature, and Tc or higher temperature, or the hotter side temperature, and Tc is nothing but the uh, cold temperature. Okay, now what happens here is when the heat flows, okay, so from the naturally the heat is transferred from one end to another end. Okay, unless otherwise thermal equilibrium is achieved, what happens is you will be having a high temperature on one side, or a slightly higher temperature on one side, and lesser temperature on the other side. Okay, and this difference in the temperatures is mainly due to the thickness of the material, and similarly it is also depends upon the thermal conductivity of the material. For example, materials like wood, bakelite, etc. What will be the temperature difference from one end to another end? For example, wood or bakelite, especially for bakelite. We use bakelite as, especially in case of pressure cookers, handles will be made of bakelite. Why it is made of bakelite, ma?
So they are poor
Insulated.
conductor of heat.
Yes.
They are poor conductor of heat, sir.
Yeah, it's a poor conductor of heat, or otherwise the vessel heat will not be transferred to our hand. Okay, so that's why it is made of bakelite. Okay, so it's a poor conductor or it is a good insulator. Okay, bakelite is a very good insulator, so that what happens is the heat is not transferred from the vessel to our hand. Okay, so it depends upon not only the length, or it also depends upon the K value, that is thermal conductivity. Now the same equation I can rewrite it as Q equal to TH minus TC divided by L by Ka. Okay, so Q equal to TH minus TC divided by L by Ka. So that L by Ka is nothing but the thermal resistance. Okay, so the thermal resistance is usually given by the length you have to conduct and divided by conductivity, which is nothing but the thermal conductivity, and the area A is nothing but the area available for conduction. All of you are able to understand this. Ohm's law, we know that current which is equal to 1 by Re into V1 minus V2. Current equal to electrical resistance into voltage difference. Similarly, here in case of heat transfer, Q equal to thermal resistance into temperature difference, and the thermal resistance often it is mentioned as L by Ka. Okay, thermal resistance often it is mentioned as L by Ka. So thermal resistance inverse, Ka by L is thermal resistance inverse, and uh, Q equal to thermal resistance inverse into Th minus Tc, or in other words, uh, Q equal to del T, temperature difference divided by thermal resistance. All of you are able to understand this? Hello, how it is
Yes, sir.
related? Heat transferred is equal to the product of inverse of thermal resistance and temperature difference, or heat transferred is equal to temperature difference divided by thermal resistance. The thermal resistance is nothing but L by Ka. Length you have to conduct divided by conductivity, thermal conductivity of the given material, and area available for conduction. Okay, so this is what you have to understand. Okay, so composite cylinders and spheres, we will look into it. Okay, when we discuss about conduction in detail. The second one is Newton's law of cooling. So in case of Newton's law of cooling, it gives us an idea about the convection. We know that convection, it is a combo of conduction and advection. Okay, I request all the students to check what is advection and tell me in the next class. Okay, advection is usually the it refers the bulk motion of the fluid. Okay, so the energy transferred due to random molecular motions and by bulk motion of the fluid. Okay, so it involves a combo of conduction and advection, that's why the name convection. Okay, so that is from the material. For example, in case of internal combustion engines, internal combustion engines, the fins will be getting the heat energy from the engine cylinder. Okay, and then the fin tip transfers the heat to the surrounding fluid. Okay, so at the tip you will be having a combo, that is up to the tip you will be having conduction, and at the tip you will be having the fluid motion. Okay, so which is nothing but the advection. So a combo of conduction and advection, which is nothing but convection. Okay, so the energy transfer due to random molecular motions and by bulk motion of the fluid. Okay, so you may ask a question, random molecular motion, how will you say that, sir? See, I have told you the practical example of a hot coffee placed in a tumbler. Okay, when you leave as it is, okay, it will come to room temperature after say 15 minutes or 20 minutes. How it occurs? Even if you switch on the fan, sir, sorry, even if you switch off the fan, I'm sorry. How it occurs, ma? Hot coffee, when you keep it in the tumbler, after 15 minutes, it cools down or it comes to the surrounding atmospheric temperature. How?
Natural convection, sir.
Natural convection. Okay, how the natural convection happens? That's my question. Yeah, that's correct. What you said is correct.
The
When you,
surrounding temperature is lesser than the coffee's temperature.
okay, very good.
So when time goes on, the heat will be transferred to the atmosphere.
See, what happens is since the still air which is in contact with the hot tumbler, it takes the heat energy. When it takes the heat energy, the density of the air becomes less. Right? We know that uh, cold fluid will be having higher density, hot fluid will be having lesser density. Am I correct or not?
Yes, sir.
Hello.
Yes, sir.
So
So what happens here is when we have the cold air comes in contact with the hot tumbler, naturally what happens is it takes the heat energy. When it takes the heat energy, the air becomes warmer, right? And slowly it moves up, and the chill air comes in contact, right? And the chill air comes in contact with the tumbler. So a small buoyancy force is imparted, okay, and slowly the hot air will be moving upwards, and slowly the cool air will be coming inside. Okay, so that's it. This is what happens in case of the fans which we use in our houses also. The purpose of using the fan is the fan takes in the hot air from the place, so that what happens is due to the temperature density difference, the chill air from outside will be coming inside. Okay, so that's the purpose of having the fan, drawing in the chill air or high density air, or taking the low density air from the space and giving it outside, pushing it outside, so that chill air comes inside. Okay, so similarly here also what happens is in convection heat transfer, the transfer of heat is between a surface and a moving fluid. The moving fluid may be a liquid or gas. Okay, and it depends upon the application, as I mentioned earlier, right? In case of steam generators, right, in case of steam generators in nuclear power stations, I have told you, right, the hot coolant will be taking the heat energy from the nuclear reactor, and he transfers the heat energy to the cold fluid, which is nothing but the water, right? The water gets converted into steam. Okay, so it depends upon the that, especially it depends upon the fluid, okay, whether it may be liquid or it may be gas also. There are some gas cooled reactors also in some nuclear reactors. Inert gases like helium can be used as coolant also. So sometimes gas takes the heat energy and it gives it to water. Okay, so it's don't think that immediately water is the one which is always used as a coolant. Okay, we know that in case of air cooled engines, two wheelers, air is the coolant. Okay, air, our atmospheric air comes in contact with the fins and it takes the heat energy. So moving fluid may be a liquid or it may be a gas. That particular point you have to understand. Okay, when they are at different temperatures, the rate of heat transfer is given by Newton's law of cooling. So again, Newton's law of cooling says that Q equal to Ha del T, or Q double dash, which is equal to here heat flux. Okay, the heat flux is watt per meter squared. So H into Ts minus T infinity, where Ts minus T infinity is nothing but the Ts is surface temperature and T infinity is nothing but the surrounding fluid temperature, assuming that surface temperature is greater than the surrounding fluid temperature. Okay, so and this H is nothing but the convective heat transfer coefficient, which we get from the equation, or Newton's law of cooling states that the heat transferred, right, the heat transferred from a high temperature surface to a low temperature body, right, is directly proportional to the area which is normal to the flow of the flow area, as well as the temperature difference. Okay, so the heat transfer directly, the convective heat transfer is directly proportional to the temperature difference and the area which is normal to the flow. Okay, or sometimes it is mentioned as flow area. Okay, cross sectional area of the flow or flow area. Okay, and Q directly proportional to A into del T, or Q equal to HA del T. Okay, so this H is nothing but the convective heat transfer coefficient, which we get from Newton's law of cooling. Okay, and again the convective heat transfer coefficient Q convected, which is equal to Ha del T, or heat transfer, which is equal to 1 by Ha into Ts minus Tf. Okay, that 1 by Ha is nothing but the convective resistance. Please students, please understand that conductive resistance is L by Ka and conductive resistance is 1 by Ha. Students, all of you are able to understand this? See, this is the difference between these two. Conductive resistance is L by Ka. Length you have to conduct divided by conductivity into area available for conduction, and convective resistance is, or convection, is equal to 1 by Ha. Is it okay, ma?
Yes, sir.
Yes.
Between a solid and the fluid. Okay, the conductive heat transfer coefficient of the fluid is very much important. Okay, now you can look into here. In case of free convection, gases will be having 2 to 25, and liquids will be having 50 to 1000. And in case of forced convection, gases will be having 35 to 250, and liquids will be having 50 to 20,000. And with phase change, you will be having either boiling or condensation. You will be having 2,500 to 100,000. watt per meter squared Kelvin. Okay, so liquids will be having higher convective heat transfer coefficient. That's why, especially for cooling purposes, in case of nuclear reactors or in case of steam power plants, we use hot fluids, okay, hot liquids, not hot gases, because the manner in which the heat is transferred from from the fluid to the turbine material. For example, a hot steam to the turbine blades is much more higher when compared to when we use a what's that um, uh, when we use some other materials, so some other gases, inert gases. Okay, steam will be possessing more conductive heat transfer coefficient when compared to other gases. Okay, so that's why steam is used often. Steam turbines were used for power production. Steam turbine and countries like India, we use steam power plants for majority of power production. For around 70%, 60 to 70%, or around 75%, we depend on steam power plants for power production. Okay, because the conversion of liquid to gases and conversion of liquid to vapor and conversion from vapor to liquid, it takes place, and it's easier, as well as it's what to say, we can reduce accidents when you use water. That's the advantage in going for steam power plants. And you have to understand. And one more thing, why the force convection value is higher for H value is higher, ma? Anyone? Why the force convection value is higher? Students, anyone? Force convection here, convective heat transfer coefficient value is higher. What is the reason?
Sir, the molecules are more closely packed.
Molecules are more closely packed, or the fluid is important a motion, right? You transfer. See again, the take the example of coffee. When you want to cool it, all of a sudden you will be transferring the coffee from one tumbler to another tumbler. That's why wala usually does that, right? He transfer fluid from one tumbler to another tumbler. So if bulk motion is important to the fluid, okay, transfer of fluid from one vessel to another vessel at a faster rate, automatically the Reynolds number increases, right? You impart a velocity, okay, greater the velocity, greater will be the heat transfer. Okay, so in case of force convection, naturally the heat transfer value is higher. Okay, so the next one is Stephen Boltzmann law. Again, it states that the emissive power of a body is directly proportional to the fourth power of its absolute temperature. Okay, and EB equal to sigma Ts power 4, where sigma is nothing but the Stephen Boltzmann constant, or EB directly proportional to T power 4, or EB equal to sigma Ts power 4. Okay, so this is the radiation law. Okay, so these three laws are very, very important. Stephen Boltzmann law, and then Newton's law of cooling, and then uh, Fourier law of conduction. Okay, students, I think these three laws were there, and small numericals will be there in module 1, and this ends the module 1 actually. Okay, module 1, this is module 1, and module 2, we will be discussing about composite systems. So, when you come for next Monday's class, all of you please bring that heat transfer data book. Is it fine, students? With this,
Yes,
I
sir.
stop the recording.
Yes, sir.